Hello. The other day I was trying to figure out how to make an object, well, a plane to be specific, face its movement velocity. So what I mean by that is if you look at this particle system here, um, you have little sparks that are kind of flying out, and any way you look, they're facing the direction they're moving, right? Um, and this is happening because the planes that are representing each of those sparks are rotating to face you, right? So anyway, I was trying to do what Niagara did, and I struggled a bit. So I thought I'd make a video talking about how to do that. Um, so the first thing you probably want to do would be to make a actor and do this just with code before you try to do it in a shader. Um, so let's do that. So I'm just going to make a new blueprint actor, call it test facing, and let's see. So this actor, it's going to have a static mesh. This is just to demonstrate, and we're going to want to use a plane from the engine content that's on the ground, like this. Let's make sure that's the like 100 by 100 one, and in fact, it is. Okay, so if you look at this plane, you'll see that its forward direction is x, its up direction is z, and its other axis is y in the left-handed axis system that Unreal uses. So let's first, we're just doing this for demonstration, so we're not worried about performance. So we'll just use tick to move it. So first thing we want to do is let's just make a velocity to make the thing move, right? So let's make a vector, and let's make it move, let's say just straight up to start with. Okay. So we can make the actual actor move with add actor world offset like this. So we would just take our velocity. If you hold control, you can do get without having to do this. And alt will actually get set. That's a cool little handy thing to know. So we go multiply velocity by delta seconds, and we just add that to our location, right? Okay. So let's go ahead and look at what test facing looks like if we drag it in the world then. All right, so there it is. And if we simulate, you'll see it's moving up, right? That's how we expected it. Okay. So let's draw a debug arrow to represent our new direction we want. So if it's going to move in the x direction, let's draw our new x-axis, which is going to be in the direction of velocity, right? So we would want to normalize this if it's going to be an axis. And let's see. Our debug arrow would start at our get actor location, right? And it would end at get actor location plus this vector times some amount. Let's make it 100 long, right? Let's go ahead and move this up out of the way. And let's go ahead and make it red for x. Okay. Now if we simulate, we can see our x direction pointing like that. Okay. So why don't we go ahead and try to use some functions to set the actor rotation, right? So we can set actor rotation with this node on tick, and you can see it needs a rotator. We can make a rotator from x, if you see. So if we just give it our velocity direction and tell it to set the rotation from X. Let's see what happens. Oh, so you look, X is now facing the direction of movement, but as you can see, that plane is not rotating to face us, right? So it's moving, it's facing the direction of movement, but we would want that plane to face us. So what would that mean? Well, that would mean that the static mesh's Z, which is the up, is trying its best to face the camera, right? So how would we do that? Well, let's get the player camera manager. Let's see. And we can get the camera location from that. And then we would subtract. So we want a vector to the camera from the actor's location. Okay. And then we would normalize it. Okay. So this vector will be to the camera from the actor in the world. And if we think, well, we can go ahead and make that the z-axis. Let's make a rotation from xz, right? Why not? So we can use our x. This can be our new z. What happens if we do this? I think we have to actually play in the viewport for the camera to exist instead of simulate. So if you look, it's facing us now. But if I get down below it, it's not doing exactly what you would expect. Or let's make it move maybe in the x, y, and z. That's doing a pretty good job, isn't it? I don't think this is the right way to do it, really. Well, I mean, you don't have, I guess you could just do it this way. But I think that we would more accurately want to do something a little bit differently, which would be, so if the vector is going this way for x, or well, no, this way for x, and you want the vector that's coming towards the camera from here, right? We could project it onto the plane that x is making as a normal. So if x is this way, right, and it's a normal, then the plane would be right here that would be created using it as a normal, and that plane, any vector on that plane would be 90 degrees from x, right? So what I like to do is to take this this vector, and we can project it onto the plane, right? And then we use the x as the normal. Then we normalize it again. And that would give us our real z. That would be the z without like it being not 90 degrees. I'm guessing make rotation from xy has some kind of like tolerance for that, which is kind of interesting. All right, so you can see it's moving in the direction of velocity and it's facing us. Let's go ahead and make our y-axis as well. So forward would be x, z would be up. Okay, so we're gonna, to make the right, we can just do a cross product. So what we would do would be do the cross product of this camera vector and this directional vector. Now if we take the cross product of that, There we go. So we built all our axes. Why don't we go ahead and draw the others too, so that we can see that they're all doing what we expect. So Z is blue. Might as well duplicate those nodes. Go ahead and put that into line N. So start would be the actor location. Line end would be the actor location plus the axis times 100, which would be this guy. There we go. Let's do this one more time for our y-axis to make sure everything's looking good. Y-axis looks green. So the start will be the actor location, end will be the actor location plus the axis times 100. There we go. All right, let's see if we get what we expect. All right, look at that. Okay. So you see that plane is best pointing at us, at the camera as it can, and it's moving in the direction of velocity, right? So if we were to scale this, let's do like, as a spark. All right, here, let's put the default sprite material on it, which is what Niagara uses for sprites in default. So now if we scaled that guy, let's take a look. There we go. So look, it looks like a sprite moving in the direction of velocity and facing us as best as it can. All right, so we succeeded in making the blueprint version. What if we want to do this in a shader with world position offset, which is what I wanted to do in making my own particle systems, as you can see over here. All right, well, now that we have a blueprint version of it, it should be fairly easy to just make it in a shader, right? All right, well, let's make a new material to do that. All right, let's make it unlit. We can make a sphere mask. And we'll use the texture coordinate to drive the sphere mask. Right, make that radius 0.5, hardness 0. Now if we look at that, that's what we expect. Let's set this blend mode to additive. Maybe masked just for ease of seeing. There we go. Okay, so we made a sphere mask in the material so far. Okay, so the first thing we would have would be the direction, right? The velocity direction. The velocity. Remember, so let's just set that to 10, 10, 10 like we had before. So if we normalize that, we'll have our forward direction, right? So what I like to do is do add named reroute and just go ahead and label it that way, right? So we have that. See, another thing we can do, we can go ahead and move it in world position offset. So let's take our time. We'll frac the time so that it only goes 0 to 1. We'll multiply that times the velocity. then we'll put that in here. So you can see it's moving. See? Okay. So we made our forward. Now we need to make our up, right? So to make our up vector, we get our camera position and world space, just like we did. We're going to subtract from it our object position. Right, so that's basically like actor location that we did before. Camera position minus that. We're going to normalize it. Then we need to project this vector onto the plane. So to do that, we take the forward vector and we subtract from it. Wait, no. Reverse. We take the vector that we want to project, so we subtract from it. The dot product of these two vectors so forward is the plane normal, right? So we're taking the dot product of that, multiplying by that, subtracting that. So that should project it onto the plane. You can Google like projecting a vector onto the plane if you want to see the math for it, or this is going to be painful. Why don't I do this? Let's look in the Unreal Engine source and we can check it out real quick. So this is a good way to, when you're not sure what to do, or you know what you want to do, and you know there's an Unreal function that does it, but you don't know what the math for it is. What I do is I just do a Control F, Control Shift F, and then I do, alright, project vector onto plane. There we go. You can see here's where it's being done. And once it loads the project, I can jump to this. There we go. Alright, so you see the vector minus the vector projected onto the normal, right? So that would be our camera vector minus the projection, which is the normal times the other vector dot the normal. Yep. So normal vector times the other vector dot subtract. So that should be projecting it onto the plane. All right. So that will get us, better normalize that. That would get us our up, right? Okay, now that we have that, we're going to need our y vector, which we're going to get from a cross product. So we cross product our up with our forward, right? I'm not sure if right's the right term for it, but we'll use it for now. Because technically speaking, Unreal uses the left-hand coordinate system, you see? So y is not right, it's left. But regardless, if we wanted to flip it, we could just flip the cross here. But I know that this is correct. If you do a cross product, it's usually done in the right-hand rule. So like your pointer finger would be pointing on X, your second finger would be pointing on Z, and your thumb would end up pointing in Y. So it's definitely this direction. So up, cross, forward would get you, yeah, it would get you right. Okay, so now that we've done that, we have our three vectors. How do we transform this? So you just use the transform matrix function. There it is. And our new basis is going to be forward for x, right? Up is going to go into z, right? And right is going to go into y, like this. Okay? Let's see. This velocity is going to get added. Okay, so we're going to transform this matrix, but we need a vector to transform. So what are we transforming? Well, we're transforming the vectors that go to the points in the plane. So if we get the world position of those points, let's see, since the plane is laying flat on the ground in xy, right? I'm just going to use that. So I'm going to subtract the xy location from the object position and xy as well. So we only care about the distance or the vector on the 2D plane, right? Okay, and then we need to append a 0 so that we get a 3D vector. Okay. And then now our plane should be transformed. But to use with world position offset, we're going to have to move it to the right place in the world. So to do that, we have to add object position. And then we're going to have to subtract world position from it to get it to be an offset. And then, God. Well, something went wrong. Okay, add object position, subtract world position. Let's just get rid of this for a minute. Transform matrix, let's see. Got world position, got xy minus the object position. Appending the 0. Let's see. Make sure. There's my velocity. I'm normalizing it to get my forward vector. Oh, you know, one thing we should probably do is turn on two-sided. All right, there we go. So we can see both sides in case it flips around backwards. Although that clearly isn't the case. This is the plane normal. Let's put it on that plane in the world. we put this plane here in the world, and we put test facing on it. Oh, there we go. It's working. For some reason, it's invisible here, which is a bit interesting. You can see we can move it. All right, well, do this. We should have it moving in the world a little bit. There we go. Okay. So that's working, although it's uniformly scaled. So how would you scale it? Let's think about that real quick. That'll be the final thing we'll do. So the right place to scale it would be here when you're building these. So let's go ahead and spread this out a little bit. And we'll just add a multiply here, which will multiply it before being transformed. And we'll add a scale. All right, so if I make it 1, nothing will happen. Let's make it 4 by 1. There you go. So you can see it's now scaled. All right, so you could turn this into a material function and use it to just set the WPO of a particle if you wanted to. And in fact, that's what I did here. So here's my material function for setting world position to make a particle go in its forward velocity direction. Anyway, I hope this helped. If anybody ever tries to make something move in its velocity direction and face the camera, enjoy. One last thing I was going to say. These particle systems that I built is all based on Ben Cloward's awesome YouTube channel stuff, if you just search for him. Thanks.